What's up, amazing coders? Are you ready to level up your coding skills? Today, I'm going to turn you into master in BFS algorithm. I will teach you 5 essential applications of BFS that every coder must know to crack coding interviews and contests. Just as you can't excel in math without understanding basic formulas, you can't truly succeed in coding interviews and contests without mastering BFS and its key applications. In this video, I'll walk you through everything you need to know about this algorithm. We'll start with detecting the height of a tree, calculate the number of connected components, move on to finding bipartite graphs, uncover how to detect cycles, and finally, we'll tackle the shortest path problem. By the end of this video, you'll have all the tools you need to crush a BFS-related challenge that comes your way. And here's the best part. At the end of this video, I'll share a few secrets to get the absolute best output from these BFS applications. So, stick around, because this is going to be a game changer for your coding journey. Quick reminder, if you missed the first part of this video, make sure you watch that first. Okay, cool. Let's start our journey. BFS works level-wise. Each level's nodes are processed before moving on to the next level. As an example, it handles all the tasks at level 0 first, and only after completing those, it moves on to tackle level 1. This systematic approach ensures no node is left untouched as it progresses through each level of the tree. Cool. Imagine we have 2 connected nodes. If we know the distance of one node, we can easily determine the distance of its neighboring node. If the distance of one node is d, the distance of any adjacent node will be d plus 1, since it's just one level away. To illustrate, consider node 0 at level 0. Its neighboring node, node 1, is in level 1. Both are connected. As node 0 is in level 0, this node will be processed first, and let's say its distance is d. So its neighboring node 1 will then have a distance of d plus 1 as it's only one level away from its parent distance d. Similarly, all other nodes directly connected to node 0 will also have a distance of d plus 1. Let's find the maximum depth or height of the tree. We know the source or root node's height is always 1. Let's define the source node as p. So what would be the height of all its adjacent children? It would be the height of its parent plus 1. As they are only one level away, we will add 1 with their parent's height. It's 2 in our case. Similarly, it's 3 here for all the children at level 3. If we know the height of each node, we can easily find the distance between any 2 nodes. Let's say node 0 and node 6. If we subtract distance 0 from distance 6, we will get distance between them. Cool. We fix the height of each node. Now how can we get the maximum depth or height of the tree? It would be simply maximum height among all of the nodes' height. To be more clear, let's see in code. Let's consider an array to store the heights of the nodes, initializing all node heights to 0. Since the height of the source node is always 1, we'll set it to 1. Here we will get the current node means current parent node. So we can also get the parent node's height. Cool. Now for all its adjacent nodes or child nodes, we will add 1 with their parent's height. In the output, we should see the height of each node. Great. To get maximum depth or height, we can simply take maximum height among all of the heights. Let's see the output now. We can see the maximum height is 3 in our tree. It's really cool, isn't it? To find connected components in a graph, we will iterate through each node and use each node as a starting point if it hasn't been visited yet. We'll then attempt to visit all nodes connected to this source node. If we encounter an unvisited node after completing a traversal, it indicates the presence of another component or subgraph. Let's see an example. We will start by visiting node 0. If we manage to visit all nodes in the graph starting from node 0, it implies that all nodes are part of a single connected component, meaning there is only one connected component. Cool. Here we just need node 0 to traverse the whole tree. Let's see a graph with multiple connected components. Here we will start visiting from unvisited node 0. This traversal will only cover one portion of the graph, leaving some nodes unvisited, indicating the presence of additional connected components. We need to visit it via node 1. It will traverse all its connected nodes. Okay, great. Now all nodes are traversed. We needed 2 nodes, 0 and 1 as source nodes to traverse the entire edges. So we have a total 2 connected components. Let's write some code. Initially, we have 0 connected component. Let's iterate each node and pass it as the source node. This source node will traverse all edges for its own component. Cool. Make sure we are passing source node which are not visited yet. In each iteration, if the node is not visited, we can consider it as a new component. So we will add one more component with the total component. Now let's see the output. We have 1 connected component. Okay, delete this node, 0, 1 now. We should get 2 connected components. Yes, it's what we expected. Cool, isn't it? Can we represent this tree with 2 colors so that no adjacent nodes have the same color? Let's try. We can see there is no adjacent node with the same color, so it's a bipartite tree. Awesome. Let's add an edge, 4, 5. So they are now adjacent nodes. Also, they have the same color, so it's not a bipartite tree. Let's write some code to detect whether a graph or tree is bipartite or not. For simplicity, let's make it colors. Initially, all are -1 means we did not color any nodes yet. We will try to color each node 0 or 1. If any 2 adjacent nodes have the same color 0 or 1, then it's not bipartite. First, let's color the source node with 1. Okay, now here we will get parent node's color. So we have to make the opposite color for all of its children if they are not colored yet. So what should be its child node's color? If parent color is 0, then children will have 1. And if the parent's color is 1, children will have color 0. This will ensure its children's color is opposite than its parent color. Let's take a look here. Parents can be 0 or 1. As we will XOR them with 1, if parent is 0, child will be 1, and if parent is 1, child will be 0. Great. This is how we will ensure opposite color to all the children using XOR. We will color the child if it's not colored yet. Great. Now if the child is already colored, we should check if it has the same color as its parent or not. If it has the same color as its parent. So it's not a bipartite tree, as both adjacent nodes have the same color. After checking all the nodes, if there are no 2 adjacent nodes with the same color, we can call this tree or graph a bipartite graph. Let's see the output now. You can see it's bipartite graph. Now let's add nodes 4 and 5. It should not be a bipartite graph. Let's see the output. Yes, it's not a bipartite tree. Awesome. We did a great job. We learned how we can detect if a tree is bipartite or not. Are you ready to unravel the logic behind cycle detection? Let's dive into it and see how we can detect cycles in a graph using BFS. Imagine we start with node 1 and begin visiting all its adjacent nodes. First, we visit node 4, mark it as visited, and keep track of its parent node, which is node 1. Next, we visit node 5, mark it as visited, and again, we note its parent, which is also node 1. Now let's say we try to visit node 5 from node 4. We see that node 5 has already been visited. But why is it visited? Of course, it was visited earlier by some other node. In this situation, we can say there is a cycle present. Now let's break down the logic behind this and see how we can use it in our code. We will see an example. Before that, let's discuss a few important observations that's required for detecting cycles. Basically, based on these observations, we will detect cycles. We know that parent nodes are marked as visited before their children. This means that during BFS, we first mark the parent node as visited and then its child nodes. This is a fundamental behavior of BFS. Now let's consider an example. Let's say we have 2 nodes U and V. Define U as parent and V as its adjacent child. We will visit parent first. Let's mark it visited. Then we will explore the child. As it's unvisited, mark it as visited. Now here's the critical observation. When we explore all adjacent nodes of V, we might find that U is already visited. This is normal, as U is the parent of V. But see, there's no cycle here. The key is to check whether the visited node U is the parent node of the current node V or not. If we find a visited node and at the same time it is the parent node, then we know there's no cycle like here in the example. However, if we encounter a visited node that is not the parent node of the current node, then we have detected a cycle like what we saw in the first example. This is the logic we'll use in our implementation. By keeping track of each node's parent during BFS, we can effectively detect cycles in a graph. Okay, great. Let's come back to the first example again. Let's say our current node is 0. We will visit node 1. Here notice node 0 is already visited as it's the parent. Now we will visit its child 1. Cool. Now let's see. When we will explore all the adjacent children for node 4, we can see node 1 is visited. And node 1 is the parent node of 4. So it's a valid scenario. But another adjacent child 5 is visited already by node 1. So when we explore it from node 4, we find it visited. At the same time, it's not the parent node of 4. As we know, when we find an adjacent node visited, this adjacent node should be the parent of the current node. But here 5 is not the parent of 4, so here we detect a cycle. To detect a cycle, we need to keep track of a node and its parent node. So we'll use a pair to store a node and its parent. Initially, the source node has no parent, so we will push -1 as the source node's parent. Now here in the queue's front item, we have 2 items available. First one is our current node and the other one is its parent node. Okay, cool. Now if a node is unvisited, we will simply push a node and its parent node. Here the current node is parent of all the adjacent nodes. Great, but if this adjacent node is already visited, we have to check if this node is the parent node or not. If it's not the parent node, we can say there is a cycle. If there is no cycle found within the entire node's traversal, we can say we did not find any cycle. Awesome! Let's run the code. We can see there is no cycle. But if we add an edge 4 and 5, there should be a cycle. Let's run the code again. Yes, it's detecting the cycle properly. Awesome! We learned to detect cycles. Let's assume we have node 0 as source node and node 7 as destination. We want to find the shortest distance between those 2 nodes. Initially, let's assume each node's distance is infinity, as we don't know the exact distance of a node. Cool. But can define the source node distance 0 as its source node and the starting point of the destination. What would be its adjacent node distance, which is 1 level away? Its parent distance plus 1. Of course, it's distance 1 for node 1, 2, and 3. And similarly, it's 2 for its next level nodes. Now we know each node's distance. We can print the destination's distance. It's almost the same as what we saw in finding the height of the tree. There we checked only visited or unvisited nodes. Here we checked if nodes had infinite distance or not. Awesome! Let's code now. We will define all nodes' distance as infinity or large number, since we don't know the exact distance of a node initially except node 0. We will start our first move from node 0. It's our starting point to our destination. Let's define its distance as 0. Now here we will get parent node's distance, and here we will check if its child or adjacent node's distance is infinity or not. Infinity means it's not visited yet. We will add 1 with its parent distance if it's not visited. Okay, now we will get all nodes' distance from node 0. Let's pass the destination node and print its distance. Let's check the output. It should be 2. Cool. So from node 0, node 7's distance is 2. We found the shortest distance from any 2 nodes. Now let's find the shortest path. We know the source node doesn't have any parent. Let's put -1 as its parent node. Now if we go to its adjacent node 3, what would be its parent node? As node 3 came from node 0, node 0 would be its parent node. And 7 came from node 3, so it will be the parent node of 7. Now we know each node's parent node. How can we find the path from source to destination? Okay, let's iterate from destination. Its parent is node 3, so we will go to 3. Now what is the parent of node 3? It's node 0, so we will go back to node 0. Now what is the parent of node 0? It's -1. We know only the source node has the parent -1 among all the nodes from source to destination, so we will terminate the process. Isn't that amazing? Let's dive into the code and print the shortest path. First, we'll initialize all parent nodes to -1. Then here we will push each adjacent node's parent, which is the current node or front node of the queue. To start building our path, we'll add the destination node first. Then we'll trace back to its parent and continue this process until we reach -1. Finally, we'll print the path in reverse order since we traced it from destination to source, but we want the path from source to destination. Let's run the code and see the results. Here we have the path from node 0 to node 7. First 0, then 3, and finally 7. That's exactly the path we were looking for. It's time to reveal secrets to become truly master in BFS. Understand how those applications work theoretically, and then dive into the code. Choose medium-level questions. Remember, quality matters a lot. So pick good quality problems so that you can learn from them. Don't throw away those codes after learning. These are gold mines. Use them as black box for next BFS problems you will encounter. Means save those codes on GitHub or somewhere and copy-paste those codes in the next BFS problems you will solve. Customize codes as you need. Revise those BFS applications, as these are the base of any BFS problems. You should revise those after a few days or twice a month at least, until you are an expert in it. After getting comfortable with BFS, move on solving hard problems. Even if you can't solve it yourself, take help from a solution or video. This is how you will learn advanced techniques on BFS. If some parts of the video feel unclear at first, don't worry. Go ahead and re-watch it until everything clicks. Concepts like BFS applications take time to fully grasp, and it's completely normal to revisit the material. Trust me, the more you re-watch, the clearer it'll become. Learning algorithms isn't about getting it all in one go. It's about building understanding step by step. Remember, once you fully understand the fundamentals of an algorithm, you will be truly master in BFS and solve any problem you will encounter in coding contests and interviews. Awesome, we learned a lot. Now it's coffee time. Thanks for watching. If you found this video helpful and want more tips, tricks, and coding tutorials to level up your skills, don't forget to hit that subscribe button. Your support helps and motivates me to keep creating valuable content for you. Let's master algorithms together. See you in the next video.